Thank you very much for the kind introduction, and actually, thank you very much for the talk we just had, because my talk will go in the exact same direction, but less connected to digital twins, but to use ground truth motion to estimate your motion estimation algorithms. But before that, let's discuss a little bit why we use computer tomography. So in material science, I probably don't need to tell you that for materials, we get great insight into materials microstructures by computer tomography, and we can resolve materials on a very fine scale. And we can do all of that non-destructive, which is really powerful because we don't need to destroy our material to find out what's going on the inside. But now the question is, of course, our materials behave. They need to be stable under any kind of load, usually. So what is with the motion? Can we resolve that in a particular same manner? And how to estimate this or how to investigate the material's behavior is by in situ material tests. Just if you are not familiar with them, they can be, they're usually a material test coupled with any kind of imaging modality. I would say the state of the art at the moment is X-ray computer tomography, but you can also think of synchrotron or something else. And what is usually happening is that you perform a material test inside the CT, and you do not do this continuously, but quasi-static. That means you once scan the undeformed sample, then you compress it a little bit, you keep the load steady, and then you scan again. Of course, there are already procedures to do that continuously, but usually in computer tomography, you better do not move anything because it gives you artifacts. So quasi-static is the classical way to do, I would say, at the moment. This way, you end up with a time series of images, of 3D images. And between the images of these time series, you can estimate the motion. And that's the motion is usually estimated by a minimization problem. You saw a very similar one in the last talk, but there's a slight difference. I'm not sure. So there's a slight difference because there's a regularization term now on the right. You can cast almost all of the motion algorithms into this context. And we just heard about DVC, but in general, you can split all of the motion estimation algorithms into a distance measure and a regularization, also the classical DVC ones. Now, in regularization, classical DVC methods put their focus on subdividing the image domain omega. We had this with the subvolumes just now, and the transformation, which can be fairly general, but you saw in the last talk, displacement is, for example, one that is very commonly used. And then there are, let's say, 3 methods. There are, of course, many more, but 3 main methods to divide DVC. The first one is the local one that we just saw by subdividing the image into subvolumes and calculating a displacement vector per subvolume. Then there's global DVC, where we subdivide omega by a finite element grid, and we solve for node displacement. And in 2020, there was a combination introduced, which, from my perspective, or what I saw, performs very powerful among the open source softwares. In Kaiserslautern, we actually do motion estimation a little bit different because we focus on the regularization term on the right. What we do is we use a fairly well-known regularization from 2D image processing, and it's called total variation. It originated in denoising, but was very successfully applied to motion estimation. And what it does is it removes spurious oscillations, but recovers in normal images edges, so in displacement fields jumps. And that is actually very useful if you think of what you want to see in experiments often. So things like fractures and crack can therefore be unveiled in the displacement field in the end. However, the term on the right is, from a mathematical viewpoint, a very difficult one to solve. So you need to really work around to find proper solutions. And there are generally 2 ways. One is to approximate the total variation by smooth functions. Then you solve a system of nonlinear diffusion equations. And the second one is to discretize TV. Then you can use means of convex analysis, but I will not show that today. If you're interested, feel free to ask. I can provide you with the information. Now, what you can see is that the motion estimations I picked out here are fairly different. So, what about validating them? And what I want to do now is I want to pick out 3 different kinds of ground truth displacement fields and show you how you can use them to unveil the differences in these algorithms. The first one will be a completely synthetic one. So we use a real CT image. Of course, you can see it's denoised. It's a very nice one, nice contrast. So, but it's a foam, so a spatially sparse material, and therefore one of the challenging tasks in DVC. What we do is we introduced a completely synthetic displacement field consisting of 3 components. The first one will mimic a jump, also a strong discontinuity if something breaks or fractures. The second one will be 0 to check how outlier safe our algorithms are. And the third one will be a smooth compression along one axis, what we usually see in a classical compression test. So if we now look at the images, and what you see now on the left will always be the ground truth, is that especially the discontinuity is now interesting, because we, on the one side, we proposed a motion estimation algorithm that is designed to resolve jumps and discontinuities, so that one performs really well. And on the right side, you see what was described now in the last talk, because DVC methods tend to smooth out jumps and discontinuities. So you can see in the middle that the algorithm really tries to find a smooth transition from the blue part to the yellow part with smoothing out in the middle. If we look at the 0 displacement field, I would say both of them perform fairly similar. And on the last one, you can now see also an interesting effect, because we had the smooth compression. And because the optical flow-based algorithms are designed to reconstruct functions with jumps, they will also tend towards them. So you see that the discontinuity was transferred to the third component as well. And DVC on the other side, because it's a very smooth material with smooth shape function, as we just heard, performs a little bit better here. What is now also very nice is that when you have ground truth displacement field, you can calculate norms based on the ground truth displacement field. So if you look at this table, we have 3 norms. The first one that you can calculate for every image is just a plain root mean squared error. That is one you probably have seen quite often. But we have 2 more. And the first one and the second one, they are actually norms based on how well the displacement field looks in the end. So the first one, the average angular error, is an angular deviation from the computed field and the ground truth field. And the second one is, again, a root mean squared error, but now on the components of the displacement field. But also in the choice of these norms, you need to be careful, because when you carefully look at the table, it seems that within the average angular error, the results are much closer than in the average endpoint error. And that is the case because the average endpoint error is a root mean squared error, and it's very prone to outliers. So the middle layer where the DVC methods fail, they cause a higher error. So also with simulated displacement field, pay attention which kind of error norms you use. So now that we used a fairly simulated and artificial displacement field, we can do a pretty similar step to the last talk, namely we can use simulated displacement field as ground truth. And what we used was a sample on long fiber reinforced thermoplastic to not always have foams in there, but also fibers. And we had, you can see the image size, and we are in the beginning of the plastic phase, and we have a ground truth displacement field that you can see here. And another way on evaluating how well your motion algorithms work is to look at the residuals. So to look at the slice-wise residual and check how well they performed. What you can see here, that I would say all of them are fairly similar. Of course, some of them are better, some of them have less errors, but all of them, compared to what we saw before, they perform really well. And if we now look at the displacement, well, there's on the very top, you see the ground truth, and it's very difficult to spot the differences. Again, if you carefully look, the displacement field itself was not very challenging. no jumps, no edges. So a very smooth displacement field that can be very easily met by all of the algorithms. So DVC, optical flow, all of them really performed well here. So be careful what kind of simulated displacement you choose, because it may be that it's just not too challenging to really map actual material behavior. And that is the content of the next example, because here we have a aluminium foam, or again a foam, but this time also very challenging because we have very thin struts, very large voids. These are usually the materials where you really struggle to find a proper local DVC, for example. So I think global usually performs a little bit better, but then may oversee small motion. But when you, for example, in local DVC put a subvolume exactly in the void, well, what would you do? Nothing at best, and not converging or not putting out any solution at worst. So, but again, let's compare simulations and the calculated displacement field. And on first side, in the compression direction, so this is here now from top to bottom, you can see that also in the displacement field. You see that actually all of the methods perform well. They capture the compression very nicely. But when it now comes to the other components, it seems like simulation again is a little bit too nice to the material, because it does a very natural behavior. If you compress something, of course the foam moves to the left and to the right. This is seen in the simulation, but somehow the displacement field of the calculated experiments, they give the impression that this may not be the case. And this is also for the third component. And maybe as a last point, why it is so important to really decide beforehand what kind of material behavior you want to see. Let's go to a real experiment, namely an in situ test of an open cell metal foam. And what you know about these open cell metal foams is that though they macroscopically behave elastic on the first stage, already in the elastic regimes, you may have breaking struts. And these breaking struts will eventually cause full layers to collapse. So in elastic stages, it's very important to properly map the displacement such that you can predict where the foam will fail. And if you now compare the voxel-based method by optical flow and the RDVC, you actually see exactly that happening. DVC will oversee the local failure, where the voxel-based method managed to find it. And we can calculate strain on that. And within the strain, we really see the local extrema that mimic the failing cell. And what is also very nice if you have voxel-based full field displacement is that you can use them to really follow your foam in the end, or your cell in the end while it fractures. Let me draw a short conclusion. So what we just saw is that we really need proper validation, but we also heard that in the last talk. So because if you have delicate material behavior, if your materials behave very complex, you need to make sure that everything you calculate or everything you use is also able to work, so to map what you want to see or what you expect in the end. Ground truth displacement are a great help and can be a great help, because they do not only validate that your methods work, but they also help to identify weaknesses. But handle them with care and really make sure they mimic the behavior that you want to see. And as one more takeaway message, plan beforehand what you want to see in your material tests and then choose the motion estimation accordingly. And with that, thank you very much, and I'm looking forward to your questions.